Hi everybody, it's Tuesday, October 15th, 2024. This is your skill check number 5, the midterm review. Here in this particular review, I've given you topics from chapters 1 to 8, which includes the contingency table, linear regression, the normal model, residuals, leverage points, and influential points, 5-number summary and outliers, and interpreting a histogram. So this is not comprehensive. Your midterm could include anything from chapters 1 to 8, but these are some of the key topics for you to be prepared for. And don't forget, last week we covered chapters 9 and 10 on sampling theory and experimental design. Anything from those chapters may also appear on the midterm. So think of this skill check as part, but not all, of your preparation for the midterm. So the first question is a contingency table. Here we're pretending that children were randomly selected from 3 countries and were asked to report the number of hours they spent playing console games such as Xbox per week. The data was categorized into 3 groups, 0 to 5 hours, 6 to 10, and 11 plus hours per week. And as you can see in the data. So here, clearly we're going to be calculating some proportions or percentages. As follows, the first question asked, of all the children, what proportion were from China and played 0 to 5 hours per week? So the who is all the children, that's 317 individuals. And the contingency is that these are children who are both from China and played 0 to 5 hours per week. And so here, that sample size is 75. And so the ratio, 75 over 317, gives you 23.66%. The next question was asking, of the children from China, what proportion played 0 to 5 hours per week? Sorry, I misspoke. What percentage played 0 to 5 hours per week? And so the who is the children from China, so that's 109 in total. And in this case, the condition is that they played 0 to 5 hours per week. And so that would be 75 of the 109, giving 68.81%. And finally, I think this is the last one. The question asked, of the children who played 0 to 5 hours per week, what percentage of those were from China? And so the who would be children who played 0 to 5 hours per week. That's 170 in total. And the condition is children from China. So that's 75 once more. And here we get 44.12%. Okay, so next here we see a bar graph showing the distribution across those 3 categories of playtime, one for each of the 3 countries. Now we can see that the distributions, they look different. What that means is the way the distribution looks across playtimes depends on the country. So clearly then, there is an association between these 2 categorical variables, right? So just to read what I have written here, the distribution across playtime categories looks different depending on the country. We can therefore conclude that the 2 categorical variables are dependent, or to say it another way, are associated. Next question is linear regression. Here, to assess the impact of playing console games on performance in school, the response variable grade received in a class at school was regressed onto the predictor hours per week playing a console game. So the line of best fit for 50 data points is reported as follows. So notice here, I'm not showing you the scatter plot of grade versus hours. Later, we're going to see only the scatter plot of the residuals. And this is typically the way these kinds of questions will be presented to you on, say, a midterm or a final. We can see the equation in front of us. We see grade with a hat on top of it. So that's, the predicted or fitted value for grade. We have an intercept of 70.11 and a slope of minus 2.28. So I think here we're going to first interpret what the model coefficients, what they actually mean. So the slope, we can sort of draw sort of a picture of that, and the intercept. And so what can we say about the slope? The slope tells us that for every extra hour per week spent playing Xbox, a student's grade will decrease by 2.28% on average. The intercept says that the average grade for students who spend 0 hours playing Xbox is predicted to be 70.11. Right, so I should mention, we did talk about a couple of classes ago, we talked about extrapolation. And what I told you is you should not extrapolate. What that means is if you build a regression model, there's a certain range over which you have the predictor variables in your data. You should not make any predictions beyond the range of those X values that are in your data. If you do make such a prediction, that's called extrapolation. So extrapolation is a no-no because, the linear trend may not continue past the range of the data that you used to fit the model. And that's often the case. So we do not extrapolate. Now here, you don't know if the data included students who studied 0 hours per week. And so for the purposes of this exercise, let's just assume that is the case, that some students actually studied 0 hours per week. In that case, the intercept can be interpreted because the intercept is within the range of the data. So we're not extrapolating. But if, let's say, students played at least, 2 hours per week, which means no students actually played less than 2 hours. In that case, the intercept, interpreting the intercept, would be an extrapolation. And that would be something we're not supposed to do. Right, so anyway, in this case, I didn't tell you which was the situation, but I'm telling you now that we're going to assume that some students played 0 hours per week. In such cases, it's okay to interpret the intercept if the intercept makes sense. So in this case, it does make sense. If you spend 0 hours per week playing, then on average, your score in the course will be about 70%. Okay, next we're asked about the coefficient of determination. It was given to be 83.04%. So what that tells us is that about 83% of the variation in the final grades of these 50 students can be explained by differences in the number of hours per week spent playing Xbox. And so that tells us that the remaining 17% of variation is due to individual differences. In other words, it goes into the residual part of that linear regression model. We were asked to calculate the correlation coefficient. Here, the only trick is to remember to first convert r squared from a percentage into a decimal number, then take its square root, and so doing so we get a correlation coefficient of 0.9113. Next, we were asked to predict what the grade would be for a person who studied 4 hours per week, and so we start with our regression equation. We put 4 in for hours, and then we multiply and then subtract, and we get 60.99%. So what we're saying is, on average, a person who studies 4 hours per week is predicted to be about 61%, according to this model. This is the average grade for students who play 4 hours per week. We are told that a particular student who plays console games 4 hours per week scored 63.09%. So what is that person's residual? Well, we just take the observed value minus the predicted or fitted value, and we get a 2.10%. Okay, next we're going to look at the residuals. So here we have residuals versus fitted values. The key is to look at this scatter plot and ask yourself, is there any kind of structure? If the answer is no, then the model is appropriate. If the answer is yes, then you got some problems. So what in particular are we looking for? First, we want to test to see if the linear enough condition is satisfied. And what that means is what you're asking yourself, is there a trend, linear or otherwise, in the residuals? In this case, I would say there is no trend. no obvious trend. And so the linear enough condition is met. I can tell because there is no obvious linear or nonlinear trend in this plot of the residuals. So what that means is the original scatter plot, which you haven't been shown, the original scatter plot of grade versus hours, that scatter plot would look roughly linear. That's the linear enough. And because it looks roughly linear, the residuals have no trend at all. So that's the first part. The second aspect you need to look at here is to check whether the spread in the vertical direction as you move from left to right in these residuals is roughly constant. And here it is. There is no obvious thickening of the plot or trumpeting in this case. So the thickening of the plot condition is met. I can tell because the spread of the residuals in the vertical direction is roughly the same as one moves from left to right. Moving on to the normal model. Here, you might have seen this diagram before. It was in one of our skill checks for chapter 5, I think it was. Here, we're pretending a company makes bolts that are supposed to be 9 millimeters in diameter. However, the manufacturing process is not exact, and so there is some variation. So we're supposing that bolt diameters are normally distributed with a mean of 9 millimeters and a standard deviation of 0.2 millimeters. So this mean and standard deviation, these are model parameters, and we're going to use this model to make predictions based on calculated areas. So the first part was was making use of the empirical rule. So here we have a picture of the empirical rule, and we were asked what proportion of the bolts. We were asked 68% of the bolts are going to be between what two values in diameter. And so 68% is plus or minus 1 standard deviation. And so all we needed to do here is calculate the mean minus 1 standard deviation and the mean plus 1 standard deviation. And so we can say using the normal model, we predict that the diameter of about 68% of the bolts will be between these two values, 8.8 millimeters and 9.2 millimeters. Right. I guess there's nothing else I need to say about that one. Okay, the next question was this. As I recall, it was saying that if a bolt that's made is no more than 0.5 millimeter different from the mean, the intended mean, right? So bolts are supposed to be 9 millimeters in diameter. If bolts are more than 9.5 or less than 8.5 millimeters, then those bolts have to be thrown out because they're not suitable for sale. And so it was asking what proportion of bolts are not going to be thrown out. That would be the bolts between these two values. So we need the area under the normal distribution starting at 8.5 and ending at 9.5. And so how do we get areas? We have to convert our values of interest into z-scores. So we do that for both values. So on the left, we take 8.5, subtract the mean and divide by the standard deviation, and we see that 8.5 is 2.5 standard deviations below the mean value. Likewise, when you go to the right, 9.5 is 2.5 standard deviations above the mean. And so our picture now is this, centered at 0, a z-score from 0 to the right up to 2.5, to the left down to minus 2.5. We want to know the proportion of those z-scores that are going to be between minus 2.5 and plus 2.5. Right, so let's see what I wrote here. Yeah, we need the area in between the two bounds where the absolute value of z is less than 2.5. In other words, where z is less than 2.5 standard deviations away from 0. So to do that, we can get the upper tail area, and because of symmetry, that will be the same as the lower tail area. And then we subtract those areas from 1, and we'll get the value of the area in between. That's the strategy. So first we have to go to the Z table. We're looking at 2.5 standard deviations. We see the area to the left of that Z score is 99.38, it's 99.38%, or 0.9938. So that's the area where Z is less than 2.5 standard deviations. We want the upper tail area, and so we have to subtract from 1. So going back to the diagram, the area where Z is greater than 2.5. I have a sign wrong, I just noticed. I should be saying the area where Z is... Oh no, that's right, sorry, that's right. Okay, let's just show you where I went wrong, just to make sure nobody got lost. So here, the area we're looking at from the Z table is the area to the left, but I want the area to the right. I want the area not where Z is less than 2.5 standard deviations. I want the area where Z is greater than 2.5 standard deviations, right? So we have the area less than. The area greater than, yeah, this is correct. So the area where Z is greater than 2.5 is 1 minus the score we got, or sorry, the proportion we got from the Z table. So that's 0.0062. So what I'm trying to say is the area in the upper tail is 0.0062. Now, of course, by symmetry, the area in the lower tail is the same. And so the total area in the two tails added together is just twice that area in the upper tail. So 0.0124. So what's the area in between? We just take 1 minus that number. So the area in the two tails where the absolute value of Z is bigger than 2.5 is that 0.0124. And so the area between the two tails where Z is less than 2.5 standard deviations in absolute value is 0.9876. And so it's 98.76%. And so we can say, using the normal model, we predict that 98.76% of all bolts made will not be defective having diameters between those two bounds, 8.5 and 9.5 millimeters. Right, next moving on to residuals and leverage points. Here we have a graph. We have 3 data points that look like they're far away from the rest of the data. Those are the ones we need to label. A data point that only has a large residual is just simply a data point that's far away from the line of best fit. A data point that is a leverage point is far away from the rest of the data in the x direction. And so we have 2 leverage points. The first one is not influential. Why? Because it has a small residual. So if a leverage point has a small residual, it's not going to be very influential. A leverage point that has a big residual is going to be influential. And so these are the appropriate labelings. Now I want to point something out, a bit of a subtlety here. And this is not something I asked you to do on the skill check, but I want to just bring this up. So on the left here, you see all the data apart from those 3 unusual data points. So the large residual has been removed, and the two leverage points have been removed. That's on the left. Now on the right, it's the same, except now I've included that single leverage point that was not influential. Now notice the difference in the slopes. When the leverage point is included, the slope did change. But it didn't change by very much. The change is about 20%. And so instead of saying that data point, that leverage point is not influential, it would be more accurate to say it's weakly influential, because it does make a difference in the slope, but it's only a small difference, 20% or so. By contrast, here again on the left is all the data apart from those 3 unusual data points. On the right, here we're now including the 1 leverage point that was influential. And you look at the 2 slopes, you can see that the slope changed by more than 50%. That's a very big change in slope, and so we would say this is a strongly influential leverage point. Right, so it's correct in the first instance. If we go back, it's correct to label the points as I show you here, because your only options were it's either an influential leverage point or it is not influential. But just be aware that there is some nuance to these situations. Here we have a leverage point that does make some change in the slope, and 20% is not tiny. It's a fairly large change. We will call that weakly influential. And in the second example, this is a strongly influential leverage point. So just so you know. Next question here, we got 5 number summary. So we're given a bunch of data. And here the data is sorted from smallest to largest. And we have the number of data points is 30. We have a mean, standard deviation, and then the 5-number summary. We're going to be asked some questions about this, I guess. Right, so the first question is, what is the IQR? And so that's just the difference between the third quartile and the first. So we just subtract, we get 7. Next, I think we're going to be asked about fences. Yeah, so the upper fence is the third quartile plus 1.5 IQR. So that can be calculated. The lower fence is the first quartile minus 1.5 IQR, and that can be calculated. Next, I believe we're going to be asked about, we're going to be asked about outliers. And so as we know, once we draw the fences on a box and whisker plot, outliers will be data points that are beyond the fences. So anything larger than 32.5 would be considered an outlier. As well, anything smaller than 4.5 would be considered an outlier in this data set. So looking at the actual data, we see there's only one outlier, and that's the number 4. And question 6, interpreting a histogram. If we were to describe this histogram, we wouldn't use the word symmetric or left skewed. We would use right skewed. It's clearly has potential outliers, and I just realized I missed one of the descriptors. This histogram is also unimodal. There's one dominant mode, one bump. So I should have included that in the answer. So let me just quickly make that change. And we'll go back. Right, so what are the describing words for this histogram? It's the ones that are highlighted in green. So it's right skewed, unimodal, and it has potential outliers. I think we were asked to say where the outliers were, maybe not. But anyway, the potential outliers obviously are in the bin that is furthest to the right. We were asked how many data values are between 14 and 22 hours. So you can see there's 2 bars in that range, and each of those bars has a height of 5, and so the total is 10. So 10 people, 10 students were playing console games between 14 and 22 hours per week. And I think lastly we were asked, where's the median in this data set? You might remember there was an assignment question like this. So let's just think this through again. There are 40 data points in total, which, how do we know that? We were told so if we go back a slide or two. Yeah, right there. So it says 40 high school students were asked. So the size of the sample is 40. So that means if you add up all these bars together, the height of them, you would have 40. Right, so 40 people. So what that means, the median is the average of the 20th and 21st data points. Right, so notice that the first 2 bins contain 7 plus 28. 7 plus 18, it should say. 7 plus 18 data points. Right, the first 2 bins contain 7 plus 18 data points, which you can see just by looking at the height of those bars. So that's 25 in total. So that means the median, well, the median is not in the first bin because the median is the average of the 20th and 21st data points. The median must be in the second bin because that second bin includes the 20th and 21st data points. And so we just mark that bin. That's where the median is. So the median happens to be also where the mode is in this case. And that's often the case, but not always. So I think that was the last question. Is that correct? No, there's more. There's more. What was the next question? All right, the last question I think it was, would the mean be larger than the median or smaller in this case? And so what you need to say is, I forgot there was a question about the range. The range of the data is between 0 and 34, right? Just looking at the scale on the horizontal axis, right? So the smallest value is 0, the largest value is 34, and so 34 minus 0 gives you 34 hours. Right, here it is. The mean will be larger than the median in this case because the skew and the outliers on the right-hand side are going to pull the mean toward the right. So the median, as we know, is in the bar from 2 to 6. It's in that tallest bar. The median is the same as the mode in this case. The mean is going to be something to the right of that because of the skew to the right. Oh, and that is it. So we are done. If you have any questions about this, let's see. So you can, of course, you can leave it in the comments. You can send me an email. You can ask me in class. You can ask Ray during the SI session on Wednesday, as you wish. We're all here to help. So do not hesitate to ask if you have any issues or worries. Otherwise, I guess that's all I need to say. So bye for now.